In this video, we will continue our discussion of chirality, looking at molecules with more than one chirality center. So let's take a look at 2,3-pentane diol, which can also be named as pentane 2,3 diol. So the diol means that we have two alcohol groups. They're at position 2 and 3 out of the 5-carbon pentane. So this is a chirality center, and this is a chirality center. To make it easy to compare, let's draw out our different structures where we have the methyl group on top and then the ethyl group on the bottom, so we have them all written vertically. We can have the two OH groups coming forward on the left, the two OH groups on the right, top one right, bottom left, or top left, bottom right. These are the possible combinations. Now, if we look more closely, we can see that between these two compounds, we can draw a mirror plane. So these compounds are mirror images of each other. Are they the same thing? Are they superimposable? If we slide it over to the left, then we have our methyl, carbons, and ethyl all lined up, but we're trying to put our hydrogens on our OH. If we spin this around in the plane of the paper so that our OHs are over on the left and our H's are on the right, then we'll get those groups to line up. But as we're spinning this around, that puts the ethyl group on top. So these are non-superimposable mirror images, and so we have a pair of enantiomers. Looking at this pair of compounds, we can do another mirror plane. And what you will see is that this is a mirror image of this one. Once again, if we try to slide this over, we'll get our carbons lined up, but our OH will be on the H. So these are also not superimposable on each other. So these are another pair of enantiomers. What if we compare this compound to this compound? They're different compounds because this carbon has the OH to the left, this carbon has the OH to the right. But no matter which way you turn them or line them up, they are not mirror images of each other. So what we have here is a pair of diastereomers. So remember, we have stereoisomers. This is kind of the umbrella. And then under stereoisomers, we can have enantiomers or diastereomers. Enantiomers are non-superimposable mirror image isomers, or they are stereoisomers that are mirror images of each other. Diastereomers, a pair of diastereomers, would be stereoisomers that are not mirror images. So this compound compared to this compound compared to this one compared to this one, and this one compared to this one, they are all diastereomers. Now, keep in mind, when we are talking about enantiomers, they have the exact same melting point, boiling point, solubility, the same spectroscopic and chromatographic properties. And the only difference between a pair of enantiomers is the direction of rotation of plane polarized light. Diastereomers, on the other hand, will not have the same properties. They will have different melting point, different boiling point, different chromatographic and spectroscopic properties. Now, they're both diols, and so of course they're going to have similar melting points and boiling points, but they are not identical. Furthermore, the pair of diastereomers, there's no relationship between the magnitude or direction of optical activity. So enantiomers have the same properties except for direction of rotation of plane polarized light. Diastereomers have different properties. Before we move on, let's also take a look at the RS configuration of these compounds. So if we're looking at this carbon, the oxygen has priority 1 and the hydrogen is priority 4. Then we're looking at this carbon compared to this carbon. This carbon is connected to CHO. This carbon's connected to HHH. So this one has higher priority than this one. So this would be priority 2, and this is priority 3. We are moving 1 to 2 to 3 counterclockwise, which would be S, but because our lowest priority is forward, we flip the assignment, so the top carbon is R. So over here, this one is also R. This one that has the opposite configuration, that's S, and this one is S. Looking at the bottom carbon, same thing, the oxygen is priority 1, hydrogen 4. This is still going to be priority 2 and priority 3. In this case, our carbon is connected to HHC, but this carbon is connected to OHC. So this group has priority over this group. And now we are going 1 to 2 to 3, which is clockwise, which would be R, but because our lowest priority is forward, we flip the assignment, so that is S. So this first compound on the upper left, this has the configuration 2R, 3S. This one is S, and then the bottom one is the opposite of this one here. So this one is R. We already said this one is S. This one is also S. We already said this is R. This one is also R. Now look at the relationship between enantiomers, diastereomers, and RS, where we have RS and SR, those are enantiomers. Where we have SS and RR, those are also enantiomers. So when all of the chirality centers have the opposite configuration, then we are talking about enantiomers. Now, if we look at the top left compared to the bottom left compounds, we are talking about RS compared to SS, and this is a pair of diastereomers. RS compared to RR is also a pair of diastereomers. So notice we have one configuration is opposite, but one of them has remained the same. One of them is opposite, one of them has remained the same. So if all of our chirality centers are the opposite, then we're talking about a pair of enantiomers. If not all of the chirality centers are opposite, then we are looking at a pair of diastereomers. So if we look at a compound that has two chirality centers, then those chirality centers could be RR, they could be SS, RS, or SR. So we have 4 stereoisomers are possible. Just by looking at the configurations, we know that these are enantiomers and these are enantiomers, and then these would be diastereomers, these would be diastereomers as well. In our next example, we have 3 chirality centers. Okay, so we could have RRR, we could have RRS, RSR, SRR, we could have SSS, SSR, SRS, RSS. I believe those are the possible combinations, so this means we have 8 stereoisomers are possible. And RRR compared to SSS, these would be enantiomers, these would be enantiomers, these would be enantiomers, and these would be enantiomers. This one compared to this one would be a diastereomer, this one compared to this one would be a diastereomer, etc. Okay, third example. What if we have 20 chirality centers? Well, let's do the same thing. We could have R, 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 R. We don't really want to do this, do we? That would be ridiculous. Too many combinations. So what we need to know instead is that if N is the number of chirality centers, then the maximum number of stereoisomers is 2 raised to the n. Right, so here we had 2 chirality centers, 2 raised to the second power is 2 times 2 equals 4. Here we have 3 chirality centers, so 2 to the third power is 2 times 2 times 2 is 8, and that's how many we have here. 2 to the 20th is 2 times 2 times 2 times 2, 20 times, and this is 1,048,576. So as we increase the number of chirality centers, we greatly increase the number of stereoisomers that are possible. So again, this is the maximum number of stereoisomers. The maximum number of stereoisomers is 2 to the n, where n is the number of chirality centers. Now here we have another example with 2 chirality centers, butane 2,3 diol, and once again we can write out our compounds with the different possibilities. So both OHs on the right, both on the left, top left, bottom right, top right, bottom left. And once again, we can see that these are mirror images of each other, and these are mirror images of each other as well. But we have to be careful because a pair of enantiomers would be non-superimposable mirror images. So looking at these two compounds, we cannot superimpose them on each other. If we slide this over here, then we have this H trying to line up on this OH. If we rotate this around 180 degrees in the plane of the paper, then we still have this OH would be lining up with this H. So these are a pair of enantiomers. These are also mirror images, and if we take this compound and we slide it over here, then we have the OH lined up with the H. So they don't slide over that way. But if we take this compound and let's rotate it 180 degrees in the plane of the paper. So now this CH3 is up here. Here's our carbon, carbon, and our other CH3. So I'm not flipping it over, I'm rotating it in the plane of the paper. So this is the CH3 and this is the other CH3. As I do that, that puts my OH over here and my H here. And now we can see that this is the same as this. So they are mirror images of each other, but they are superimposable. So these are not two isomers, these are the same compound. Because in this case, although we have two chirality centers, we also have a plane of symmetry in the molecule. And keep in mind, one of the ways that we can look for chiral versus achiral molecules is to look for a plane of symmetry. So what we have here, so again, these are both the same compound. This is an example of a meso compound. So a meso compound has chirality centers, but is achiral because it also has a plane of symmetry. So on the previous slide, we said that 2 to the n is the maximum number of stereoisomers, and this is the reason why. In some cases, we might have a meso compound, so even though we have chirality centers, it is an achiral molecule. So this compound and its mirror image are superimposable. So in this case, we have this, and this. We only have 3 stereoisomers. These are enantiomers of each other, these are diastereomers of each other, and these are diastereomers of each other. What about cyclic compounds with multiple chirality centers? We can look at 1,2-dimethylcyclopentane. Here we have both methyl groups coming forward, so this one is cis, and here we have this methyl forward, this methyl back, so this one is trans. So we have 2 chirality centers, but notice in the cis compound we have a plane of symmetry. And so the cis compound is achiral, and it only exists in this form, but the trans compound does not have a plane of symmetry, so we could draw its mirror image, which would have the methyl group up. I'm just going to use Me for methyl, and the methyl group back. So this is the mirror image, and if we rotate this around in the plane of the paper and try to superimpose it, we would have this methyl forward trying to line up with this methyl going back. So these are not superimposable. So what we have here then is a pair of enantiomers. And then cis versus trans, cis versus either trans, these are diastereomers. This is another meso compound. And so again, with 2 chirality centers, we end up with a total of 3 stereoisomers. 2 of them are enantiomers of each other, and then the one is diastereomers with both of them. Now let's look, for example, at 1,3-dimethylcyclohexane. And so we can have both groups coming forward. This is cis. We can have one forward, one back. This is trans. If we drew a mirror image of this one, here's our methyl and here is our methyl. So this is a mirror image, but we could pick up this molecule and just rotate it in the plane of the paper and then slide it over, and we would get this methyl group aligned on this one aligned on this one. So the cis compound and its mirror image are superimposable because, once again, we have a plane of symmetry that goes right through this molecule, which means this is another meso compound. So cis 1,3-dimethylcyclohexane only exists one way. It does not have an enantiomer. Looking at trans, if we draw the mirror image, now we have this methyl group here and this methyl group here. If we try to rotate this molecule in the plane and then line it up here, we can get the ring to line up and the methyls will be attached to the same carbon, but they'll be going in opposite directions. If we pick up this whole molecule and we flip it over like a pancake, then that puts this methyl group back on top of this one in front on top of this one in back. So these 2 compounds are not superimposable, which means what we have here is a pair of enantiomers. Now this gets even more challenging because in addition to these 3 stereoisomers, where here's a pair of enantiomers, these are diastereomers, these are diastereomers, we also have a variety of chair conformations that these different compounds can adopt. So we need to be able to distinguish a pair of diastereomers and a pair of enantiomers and different conformations of any of those compounds. Now, what about biomolecules with multiple chirality centers? So with menthol, we have 1, 2, 3 chirality centers. So 2 to the third, we have 8 stereoisomers are possible. With cholesterol, we have 1, 2, 3, 4, 5, 6, 7, 8 chirality centers. So 2 to the 8th, this gives us 256 stereoisomers are possible. But Mother Nature makes only one of each of these. The enzymes that are responsible for biosynthesis, so synthesizing these compounds naturally, are very specific. We had talked earlier about how it's difficult to be able to make only one enantiomer, but Mother Nature can do that with complete selectivity. So we are not walking around with 256 different versions of cholesterol in our bodies. We just have one version of cholesterol. Mother Nature is very specific when it comes to stereochemistry.